Upgrading an electrical grid to 26 kilovolts involves several considerations. It's important to weigh the pros and cons carefully before making such a significant investment. The potential benefits of a 26 kilovolt system can be improved efficiency. Higher voltage systems generally experience lower losses when transmitting power over long distances. This reduction in losses can translate to lower energy costs for the utility and its customers. A 26 kilovolt system may offer improved reliability compared to lower voltage systems. These higher voltage systems are often designed with more robust components and can be less susceptible to outages and voltage dips. This can lead to a more stable and dependable power supply for the community. A 26 kilovolt system can accommodate increased demand and load growth, providing flexibility for future expansion. As the town grows and its energy needs increase, the higher capacity of the 26 kilovolt system can help ensure that the grid can meet the demand. There are also some cons of upgrading to 26 kilovolts. One potential drawback is the non-standard voltage. Only a limited number of cities exclusively use 26 kilovolts. This could create challenges when interconnecting with neighboring utilities or seeking backup power from other sources. It's essential to ensure compatibility and coordination with the wider regional power grid. The equipment costs associated with a 26 kilovolt system, such as transformers and switchgear, can be more expensive than equipment for lower voltages. This higher initial investment needs to be factored into the overall cost analysis. Upgrading to 26 kilovolts would necessitate converting all existing equipment and infrastructure to be compatible with the higher voltage. This conversion process can be disruptive, time-consuming, and costly. Careful planning and execution are crucial to minimize disruptions. A 26 kilovolt system presents higher safety risks compared to 13.5 kilovolt and 4 kilovolt systems. Proper safety protocols and training are essential during installation, maintenance, and operation to mitigate these risks. To determine whether upgrading to 26 kilovolts is the right decision, several factors must be considered. The current system reliability should be evaluated. If the existing system experiences frequent outages or voltage problems, an upgrade may be warranted to improve service quality. It is important to project future demand. If the town anticipates significant population or economic growth, a 26 kilovolt system may provide the necessary capacity to meet the increased energy needs. A thorough cost-benefit analysis should be conducted. The city should carefully assess the cost of upgrading to 26 kilovolts, including equipment, conversion, and ongoing maintenance, and compare them to the potential benefits of improved efficiency, reliability, and future capacity. Regional coordination is also crucial. The town should consult with neighboring utilities and the state regulatory agency to ensure compatibility and address any interconnection issues associated with the 26 kilovolt system. Seeking input from qualified electrical engineers, utility consultants, and the local community is essential to make an informed decision. A comprehensive evaluation that considers all of these factors will help determine whether upgrading to 26 kilovolts is the most appropriate and cost-effective solution for the town's energy needs. Let's delve deeper into the technical aspects of each of these considerations. The efficiency gains from a higher voltage system like 26 kilovolts stem from the reduction in current for a given power level. Power loss in transmission lines is proportional to the square of the current times the resistance of the lines, expressed as I squared R. By increasing the voltage, the current required to deliver the same amount of power is reduced, leading to a significant decrease in I squared R losses. This is especially beneficial for long distribution lines, where these losses can be substantial. To quantify these efficiency gains, engineers use load flow studies to model the existing and proposed systems under various load conditions. These studies can predict the reduction in energy losses and the corresponding cost savings. However, it's important to account for the losses in transformers, which also contribute to the overall system losses. While higher voltage transmission reduces line losses, the transformation process itself introduces losses. The reliability of an electrical grid is often measured by metrics such as System Average Interruption Duration Index, or SEDI, and System Average Interruption Frequency Index, or SAFE. SAIDI represents the average outage duration per customer, while SAFE represents the average number of outages per customer. A more reliable system will have lower SAIDI and SAFE values. A 26 kV system can improve reliability by using more robust equipment, such as higher rated insulators, surge arresters, and switchgear. These components are designed to withstand higher stresses and are less prone to failure. Additionally, a 26 kV system can facilitate the implementation of advanced protection schemes, such as fault current limiters and adaptive relaying, which can quickly isolate faults and minimize the impact of outages. To assess the potential reliability improvements, engineers conduct reliability assessments using techniques such as failure modes and effects analysis, or FME, and fault tree analysis, or FTA. These methods identify potential failure points in the system and evaluate the likelihood and consequences of those failures. The ability of a 26 kV system to accommodate increased demand depends on its capacity, which is determined by the size and number of conductors, transformers, and other equipment. The capacity of a distribution system is typically expressed in terms of its apparent power rating, measured in megavolt amperes, or MVA. To determine whether a 26 kV system has sufficient capacity to meet future demand, engineers conduct load forecasting studies. These studies use historical load data, demographic trends, and economic projections to estimate future energy consumption. The load forecast is then used to determine the required capacity of the distribution system. It's important to consider not only the average load but also the peak load, which occurs during periods of high demand, such as hot summer days. The cost-benefit analysis of upgrading to 26 kV should include all relevant costs and benefits, both tangible and intangible. The costs include the cost of new equipment, such as transformers, switchgear, conductors, and insulators. The cost of converting existing equipment, such as replacing or upgrading customer-owned transformers and service entrances. The cost of labor for installation, testing, and commissioning of the new system. The cost of engineering studies, environmental impact assessments, and permitting. The cost of financing the project, including interest payments on loans or bonds. The benefits include reduced energy losses, resulting in lower energy costs. Improved reliability, leading to reduced outage costs for customers. Increased capacity, allowing the system to meet future demand. Enhanced safety, reducing the risk of accidents and injuries. Environmental benefits, such as reduced greenhouse gas emissions. The cost-benefit analysis should use a consistent set of assumptions and discount rates to ensure that the results are accurate and comparable. The analysis should also consider the time value of money, recognizing that costs and benefits that occur in the future are worth less than those that occur today. The regional coordination aspect is critical to ensure that the 26 kV system is compatible with the surrounding power grid. This involves consulting with neighboring utilities to ensure that the system can be interconnected without causing any adverse impacts. It also involves working with the state regulatory agency to obtain the necessary permits and approvals. Interconnection studies are typically required to assess the impact of the 26 kV system on the surrounding grid. These studies evaluate the system's ability to maintain voltage stability, power quality, and protection coordination. If any issues are identified, mitigation measures may be required, such as installing additional reactive power support or upgrading protection relays. The selection of equipment for a 26 kV distribution system is a critical aspect of the design process. Several factors must be considered, including the voltage rating, current carrying capacity, insulation level, and environmental conditions. Transformers are used to step down the voltage from the transmission system to the distribution system. The transformer rating should be selected to accommodate the peak load demand, with consideration for future growth. Switchgear is used to protect and control the distribution system. It includes circuit breakers, switches, and relays that can isolate faults and prevent equipment damage. The switchgear should be rated for the maximum fault current that can occur at that location in the system. Conductors are used to carry the electrical current from the substation to the customers. The conductor size should be selected to minimize voltage drop and prevent overheating. Insulators are used to support the conductors and provide insulation from ground. The insulator type should be selected based on the voltage level and environmental conditions. Surge arresters are used to protect equipment from voltage surges caused by lightning or switching operations. The surge arrestor rating should be selected based on the maximum voltage that can occur at that location in the system. The design of a 26 kilovolt distribution system should also consider the grounding system. A properly designed grounding system is essential for safety and to ensure that protective devices operate correctly. The grounding system should provide a lower impedance path for fault current to flow back to the source. This helps to quickly clear faults and prevent equipment damage. The grounding system should also be designed to minimize touch potential, which is the voltage that a person could be exposed to if they come into contact with a grounded object during a fault. There are several different types of grounding systems that can be used, including solid grounding, resistance grounding, and reactance grounding. The selection of the appropriate grounding system depends on the specific characteristics of the distribution system. The protection system for a 26 kilovolt distribution system should be designed to quickly detect and isolate faults. This helps to prevent equipment damage and minimize the duration of outages. The protection system typically includes relays, circuit breakers, and fuses. Relays are used to detect faults and initiate the tripping of circuit breakers. Circuit breakers are used to interrupt the flow of current during a fault. Fuses are used to protect equipment from overcurrents. The protection system should be coordinated to ensure that the correct devices operate to clear a fault. This involves setting the relays and fuses to trip at different current levels and time delays. The coordination of the protection system should also consider the impact of distributed generation such as solar panels and wind turbines. Distributed generation can inject current into the distribution system, which can affect the operation of the protection system. The operation and maintenance of a 26 kilovolt distribution system require specialized training and equipment. Utility personnel should be trained in the proper procedures for operating and maintaining the system. This includes training in safety procedures, switching operations, and troubleshooting techniques. The utility should also have access to specialized equipment, such as high-voltage test equipment, hot sticks, and bucket trucks. Regular maintenance is essential to ensure the reliable operation of the distribution system. This includes inspecting equipment, testing protective devices, and repairing any defects. The utility should also have a proactive maintenance program to identify and address potential problems before they cause outages. The environmental impact of a 26 kilovolt distribution system should also be considered. This includes the impact on air quality, water quality, and wildlife. The utility should take steps to minimize the environmental impact of the system, such as using environmentally friendly materials, reducing emissions, and protecting wildlife habitats. The permitting process for a 26 kilovolt distribution system can be complex and time-consuming. The utility should work closely with local, state, and federal agencies to obtain the necessary permits and approvals. This includes conducting environmental impact assessments, preparing permit applications, and attending public hearings. The permitting process can be expedited by engaging with stakeholders early in the project and addressing any concerns they may have. The cost of upgrading to a 26 kilovolt distribution system can be significant. The utility should carefully evaluate the costs and benefits of the upgrade before making a decision. This includes conducting a detailed cost-benefit analysis that considers all relevant factors such as reduced energy losses, improved reliability, and increased capacity. The utility should also explore funding options such as grants, loans, and bonds. The upgrade should be phased in over time to minimize the impact on customers. This involves prioritizing the most critical sections of the distribution system and upgrading them first. The utility should also communicate regularly with customers to keep them informed of the progress of the upgrade. The town should also consider the long-term implications of the upgrade. This includes the impact on the town's economy, environment, and quality of life. The town should develop a comprehensive plan for managing the upgrade and ensuring that it benefits the entire community. This plan should include goals, objectives, and strategies for achieving them. The town should also establish a process for monitoring the progress of the upgrade and making adjustments as needed. By carefully considering all of these factors, the town can make an informed decision about whether to upgrade to a 26 kilovolt distribution system. This decision should be based on the town's specific needs and circumstances. There is no one-size-fits-all answer to this question. The town should consult with qualified experts to help them make the best decision for the community. In addition to the technical aspects, it's also important to consider the social and political aspects of upgrading to a 26 kilovolt distribution system. This includes engaging with the local community, addressing their concerns, and building support for the project. The town should also work with local businesses and organizations to ensure that the upgrade benefits the entire community. This may involve providing incentives for businesses to upgrade their equipment or supporting local job training programs. The town should also be transparent about the costs and benefits of the upgrade and keep the community informed of the progress of the project. This can help to build trust and support for the project. The town should also be prepared to address any opposition to the upgrade. This may involve holding public meetings, conducting surveys, and providing information to the community. The town should also be willing to make changes to the project to address concerns raised by the community. By carefully considering the social and political aspects of the upgrade, the town can increase the chances of success. This can help to ensure that the upgrade benefits the entire community and is supported by the local population. The upgrade can provide a more reliable and efficient power supply for the town, which can help to attract new businesses and create jobs. The upgrade can also improve the quality of life for residents by reducing outages and improving power quality. A well-planned and executed upgrade to a 26 kilovolt distribution system can be a valuable investment for the town's future. The key is to carefully consider all of the relevant factors and to engage with the community throughout the process.